All right, so I'm going to finish up on the method of Frobenius, and this is a method for solving a differential equation around a singular point. Okay, so if we have x equal to x sub 0 is a regular singular point of some differential equation, and we had talked about the regular and irregular singular points in the last class, so you can review that in the previous notes. Anyway, if we have a regular singular point, then there is going to exist at least one solution of the form y equals x minus x sub naught raised to the power r times the summation as from 0 to infinity of some constant times x minus x sub 0 to the power n. So if we distribute that x minus x sub 0 through the summation, then we just get the summation as n goes from 0 to infinity of c sub n, some constant, times x minus x sub 0 raised to the power n plus r. All right, so r is this constant that we have to figure out what it is. All right, so it comes down to now when we're working with a regular singular point, so not only do we have to find the constant c sub n, but now we're actually having to figure out what these exponents are, what those values are. So r is a constant, the c sub i's are all going to be constant, or sorry, c sub n's are all going to be constants. And in this case, we're only going to be guaranteed at least one solution. So we'll look at the other situations where possibly you may not get a solution of this form. Okay, so there's a couple of things I want to point out before we move on and actually look at some examples. Okay, so first off, if r is not a non-negative integer, all right, so maybe it's a fraction or maybe it's a negative number, then this solution y equals the summation of c sub n times the quantity x minus x sub 0 to the power n plus r is not going to be a power series. So if r is like negative 8, then we're not necessarily getting a power series because we're going to have x to the negative 1 and x to the negative 2. So we're going to get other terms in there that don't fall under the power series definition. Also, the x sub 0 value, we're always going to let it be 0, right? So we're always just going to say x raised to the power n plus r. And also, when we are solving for r, we are in most of the examples we look at, we're going to actually get two solutions. And if we get that, then one of them will be bigger than the other one. And so we're always going to use the smaller one first. Okay, and that will make more sense once we actually start solving a problem. So let's do an example. All right, so this is example number 15 on page 239. And we're going to be solving 2x y double prime minus y prime plus 2y equal to 0. All right, so I'm going to divide the whole equation by 2x so we can get a look at our singular points, and we get y double prime minus 1 over 2x times y prime plus 1 over xy equals 0. And so x sub 0 equal to 0, that is a singular point, so that's the one we're going to be looking at. So, and I'm going to leave it up to you to verify that it's actually a regular singular point. Okay, so now the assumptions that we make are the form of y. So we're going to say, well, y is going to be the summation as n goes from 0 to infinity, c sub n, x to the power n plus r. So this is very similar to the assumptions we made when we were using the power series solutions, except for now we've got that extra term r. Okay, so if y is that summation, then we can find y prime by just taking the derivative of that term. So we get, once again, from n equals 0 to infinity, c sub n times n plus r times x raised to the power n plus r minus 1. So notice here that I'm not increasing the value of the index. So I'm not increasing that to 1, because now it's going to kind of depend on what that value of r is. Like in this case, if if n's 10, then we're saying, okay, well, n goes from 0 to infinity, but I'm adding 10 to all those values. So the exponents of x will actually go from 10 to infinity. And if r is like negative 8, which is possible, then the exponents won't be going from 0 to infinity. they'd be going from -8 to infinity. So we can't like eliminate we can't eliminate that first term. Okay, so that's y prime. So then we get that y double prime, and once again we're just going to take the derivative of the term inside. So we get that y double prime is the summation as n goes from 0 to infinity, c sub n, n plus r minus 1, and then we get x raised to the power n plus r minus 2. All right, so these are the assumptions we're making, and we're just going to plug those three values into the differential equation. All right, so I've rewritten the differential equation. So here's the differential equation, and now I'm making my substitutions for y prime, and y double prime. So here's the value of y double prime right here. This is y double prime, right? Here's the value of y prime. That's y prime. And here's what y is, right? So all I've done is I've taken my differential equation and I've substituted in y double prime, y prime, and y. All right, now what I'm going to do is I'm going to distribute any constants or anything else that I've got sitting out there. I'm going to distribute those into the summations. Now the constants themselves, like the 2's and things like that, aren't nearly as important as like in this first one we've got like an x term here. This is going to change the value of the exponent sitting up here. So now we're going to distribute all that and we'll simplify a little bit. All right, so notice what's happened here. The end effect that we get in this case is I've got a 2 multiplied at the beginning, and this exponent has changed. It's increased by 1 because I multiplied that x through. Also down here, I've got a 2 multiplied into the summation, and I'm not distributing this negative sign. I'm just leaving it out in the center. All right, now since these first two terms, since they both start with the exact same exponent, right, and the index starts the same, the exponent on the x is the same. If you remember when we were working with power series, usually we had to do some adjusting to get that to work out. But in this case, they've already matched up, and that means I can combine those two terms together without doing any other sort of manipulation. So I'm going to go ahead and do that, and I'm basically going to combine together now these coefficients, not exponents. So I'm going to have 2 times the quantity n plus r times n plus r minus 1 minus the quantity n plus r, and that's all going to be times c sub n x to the power n plus r minus 1. All right, so I've got that combined into a single term, and now I'm going to simplify those terms sitting in there so that it's a little easier to look at. Okay, so first off, what I did was I factored out the n plus r. That's right here, and that leaves me with 2 times n plus r minus 1. So that's coming from here. I just factored out the n plus r. And then I factored out the n plus r here, and that's what's leaving me with the minus 1. Okay, so then I've got 2n, so this becomes 2n plus 2r minus 2 minus 1, and then that finally simplifies, oops, not that part. That finally simplifies into what I've got here, the 2n plus 2r minus 3. Okay, now I'm going to go about extracting terms and getting this all to work out. So this first one, once again, now we're paying attention to the exponents. So I got n plus r minus 1 and n plus r. So if I plug in, they both start at n equals 0. So they're both starting at n equals 0. So if I plug in 0 for n, in the first one I get r minus 1. And in the second one I just get r. All right. So if I want these to start at the same place, I'm going to have to extract the first term out of this one, and that way they'll both be starting at n plus 1. Okay, so I'll go ahead and do that, and I'll take out the first term out of this first one. Okay, so I'm letting n equal 0, and by letting n equal 0 to get that first term out, that's going to be a 0, so I just get the term r. This term right here is going to be 0, so I just get 2r minus 3, that's right here. And then this n up in the exponent, that's going to be a 0, so I just get x raised to the power r minus 1. And now the index is shifted and it's starting at 1 instead of 0. All right, now just looking at this block, these last two, not the last two, but the two summations here, if I just look at those, now this would behave very much like problems that we had before, except for this x to the r, this r part of the exponent. So I'm actually going to factor out x to the r out of both ones. And this is a process you'll go through every time you do one of these problems. So I'm going to go ahead and factor out the x to the r. All right, so I factored out the x to the r, and notice here the exponents have been adjusted. So instead of n plus r minus 1, it's just n minus 1. Instead of n plus r, it's just n. All right, so I've gotten all that taken care of. So the next step then is we're going to look at, we're going to equate some coefficients here. I'm sorry, first off, we're going to actually go in here and make sure that these are starting at the same point, because now we can kind of treat this like we did with the power series, where I can get my start points the same, and I can get my exponents to be starting at the same place. So we'll do the same sort of ideas. We'll set k equal to whatever the exponent of the x term is. So for the first summation, we'll say k equals n minus 1, which means n is going to equal k plus 1. And then over here, we've got k equals n, which means n is going to equal k. All right, so now we'll adjust those limits in all the n values. All right, so my summations have changed. They're both starting at k equals 0, because up here, if I said n is equal to k plus 1, so I've got k plus 1 equals 1. I subtract 1, and I get k goes from 0 to infinity. Inside here, this n becomes a k plus 1, so I've got k plus r plus 1. In here, I've got 2 times the quantity k plus 1, so I'm actually getting 2k plus 2, and that will give me a 2k plus 2r minus 1 down here. This one doesn't really change, just the subscripts will all change for that second summation. So now I can write them as a single summation. So I've got k equals 0 to infinity. I've got this very long exponent, and then I've got x to the k and the whole quantity equal to 0. All right, so now we're going to equate coefficients. So first off, we have over here, we've got r times 2r minus 3 times c sub 0. We've got that equal to 0. Letting c sub 0 equal 0 doesn't do anything for us, so we are going to let r times the quantity 2r minus 3 equal 0. So we've got a little polynomial equation. So we either get that r equals 0 or r is going to equal 3/2. And then we've also got over on this side, or not on this side, but with the summation here. All right, so this summation coefficient, we're going to end up with, we get that c sub k plus 1, so I'm kind of solving the whole thing all at once, is going to equal -2 times c sub k. And that whole thing is going to be over k plus r plus 1 times the quantity 2k plus 2r minus 1. And this is all for k greater than or equal to 0, right? So it's starting at 0. Okay, so first off, so like I said when we were looking, before we started solving the problem, we said if you get two coefficients, or not two coefficients, but two values for the exponent, like we do here, 0 and 3/2, we're always going to start with the smaller value. All right, so we're going to start with r equals 0. And notice that setting r equal to 0 is going to affect the value over on the c sub k plus 1 calculation also, because you'll notice here that, you know, that's a k and that's, or sorry, not the k's, but that's an r and that's an r. So if we set r equal to 0, that's actually going to simplify whatever the c sub k plus 1s are. So if we let r equal 0, then we've got that c sub k plus 1 is going to equal -2 to the c, or -2 times c sub k, all divided by k plus 1 times the quantity 2k minus 1. So now we're going to just plug some values in. We have that c sub 0 is just c sub 0. We don't have any sense of what that value is going to be. And then we've got c sub 1 is going to equal negative 2 times c sub 0 divided by, so I'm letting k equal 1, so I get 2 times 1, so I'm just getting negative 2. Or I'm sorry, k equals 0 on this term, so k is equal to 0 here. So we get 0 plus 1 times the quantity 0 minus 1, and that's going to give me negative 1. And that'll leave me with 2 times the quantity c sub 0. All right, so if we let k equal 1, you can go through and do the arithmetic. We'll get negative 2 times c sub 0. If I let k equal 2, we'll end up with 4/9 c sub 0. And we could keep going, but we've got like 3 terms here. So let's write what solution we get from this value of letting r equal 0. All right, so to make sure we're clear where these solutions are going to come from, the first thing we're doing is we're looking at this possibility right here where we said r is 0, and we're also going to just set c sub 0 equal to 1. All right, so notice that here, if we're saying r equals 0, that'll just wipe out this first term. It won't do anything. This term right here, then we've got x raised to the power 0, so that's just going to give us the value 1, so that's not going to affect anything. So basically, we're only going to get the terms from in here. Okay, so we've already figured out some coefficients, so we'll end up with y sub 1 is going to equal, so our first solution here, y sub 1 is going to equal 1 plus 2 to the x, so that's c sub 0 plus c sub 1 minus 2 times x squared plus 4/9 times x cubed, so whoops, 4/9. So that was my c sub 3. And we could figure out more terms if we wanted to. All right, so that was letting r equal 0. So now, let's let r equal 3/2. And that'll give us c sub k plus 1 equals negative 2 times the quantity c sub k divided by, now we've got k plus 3/2 plus 1, and we've got 2k plus 2. Right, so we had 2k plus 2r minus 1, and then 2 times 3/2 is 3, so we get 2k plus 3 plus 3 minus 1, so we're getting 2k plus 2. All right, so if we clean up that numerator there a little, or sorry, denominator a little bit, we get c sub k plus 1 is going to equal negative 2 to the c sub k. Now typically, this is just, you could leave it as k plus 5/2, but I'm going to rewrite that as 2k plus 5, and I'm also factoring out the 2 from the 2k plus 2. So the way that's happening, and this isn't completely necessary, it just gives me easier numbers to work with. I'm factoring out a 2 from the 2k plus 2, and then I'm factoring out a 1/2 out of here. Right, so I'm factoring a 2, and then I'm factoring out a 1/2. So I had k plus 5/2, and if I factor out a 1/2, then I get 2k plus 5. And over here, if I factor out a 2, then I get a k plus 1. And then I've got 1/2 times 2 is just going to give me 1. So that'll give me that 2k plus 5 times k plus 1. Once again, that's not necessary. You can just work with the fractions if you want to. All right, so what do we get for coefficients here? So once again, we've got c sub 0 is just equal to c sub 0. C sub 1 is going to equal negative 2 times c sub 0. So we're letting k equal 0, so we get 5 times 1, so we're just getting 5 in the denominator, so we get negative 2/5 c sub 0. C sub 2, we get negative 2 times c sub 1. And then the denominator, we're letting k equal 1, so we get 7 times 2 is 14. So we've got negative 2 over 14 c sub 1, which means we've got negative 1/7 times negative 2/5 c sub 0, which means we're dealing with 2/35 c sub 0. And we'll get one more value here. C sub 3, so we get negative 2 times c sub 2. We're letting k equal 2, so we've got 9 times 3, so we get 27. Which means I've got negative 2 over 27 times c sub 2, which is 2 over 35 times c sub 0, which which means I'm ending up with negative 4 over 935 times c sub 0. And that's enough terms for us to express a solution. So once again, if I need the screen to move, once again, we're going to rewrite in terms of our y sub 2. So we're going to, once now we have r equals 3 halves, and we've got c sub 0 equal to 1, and that means my y sub 2 now. So once again, the r times the 2r minus 3, c sub 0, x to the power. In this case, it would be 3 halves minus 1. That term will just become 0. And so we're going to end up with, in this case, we're going to end up with x to the 3 halves times the quantity 1 minus 2/5 x plus 2 over 35x squared minus 4 over 935x cubed, and then on and on and on, whatever you get. All right, now typically we express solutions with an arbitrary constant in front. So the general solution is going to be some constant times y sub 1, and then some constant times y sub 2. And I'm using a's in this case. And normally we use c's, but I'm using a's in this case just because we had we're solving for all those c coefficients, so I don't want to be confusing like we're grabbing c0 and c1 out there. Okay, so that means I would end up with some constant a1. Whoops. So we get y is going to equal, the general solution is a sub 1 times 1 plus 2x minus 2x squared plus 4/9x cubed plus some constant a sub 2 times x raised to the power 3 halves, and then that's going to be times 1 minus 2/5 x plus 2/35 x squared minus 4 over 935 x cubed plus ... and then that's it. All right, so there's our general solution for this. So a couple of things to note about this. That equation that resulted in the values for r, so in our case it was r times 2r minus 3. This is called the indicial equation. All right, and that's where we get our values for r. It can be shown, we could show that it always works out to be r times r minus 1 plus a sub 0 times r plus b sub 0 equals 0. And this is basically, it always results from taking the coefficient of the smallest power of x, whatever that happens to be, and setting that equal to 0. So the question is, what's a sub 0 and what's b sub 0? And those actually come from those verification where we figure out whether we've got the regular singular point or not. So the a sub 0 is from the function little p of x equals a sub 0 plus a1x plus a2x squared plus yada yada yada. And the b sub 0 is from little q of x equal to b sub 0 plus b sub 1x plus b sub 2x squared plus on and on and on. And so let's look at the example that we just did so we can see what those values of a sub 0 and b sub 0 would actually be. All right, so if we look back at the differential equation we were working with, it was 2xy double prime minus y prime plus 2y equals 0. All right, we divided off the coefficient of the y double prime term. So we got y double prime minus 1 over 2x y prime plus 1 over xy equals 0. So the big P function is just the coefficient function of y prime. So that's negative 1 over 2x. And to get the little p function, if you remember, this is where we're checking for regular singular points. We just multiply by x. And so in this case, we get x times negative 1 over 2x. So we just get the value negative 1/2. Big Q is the coefficient function of y. And that's 1 over x. And for qx, we're multiplying by x squared. So we just get the function x. So that means that a sub 0 is negative 1/2, and b sub 0 is 0. Now remember, b sub 0 comes from the polynomial expansion of whatever q of x is, little q of x. So there's no constant term, and that's why we're getting 0 there. So it's like 0 plus 1x plus 0x squared, on and on. So we get b sub 0 is 0. All right, so if we plug a sub 0 equals negative 1/2 and b sub 0 equals 0, if we plug those into that indicial equation, r times the quantity r minus 1 plus a sub 0r plus b sub 0 equals 0, then we get r times the quantity r minus 1 minus 1/2 r plus 0 equals 0. And we do some distribution and some combining like terms, we get r squared minus r minus 1/2 r equals 0. And that's r squared minus 3/2 r equals 0. And then if we factor that, we get r times the quantity r minus 3/2, and that gives us the two roots. Same thing we got before, r equals 0 and r equals 3/2. So this allows you to figure out what the r exponents are. I mean, you're still going to have to go through, solving the equation. So, I mean, you'll find it anyway, but this just gives you another way of actually looking at it to find what your exponents are.